gases, it's easy for me to think of a balloon. The balloon itself isn't gas, it's rubber, but inside the balloon are gas molecules. The air we breathe is made of different gas molecules, mostly nitrogen and oxygen, but there are some trace amounts of other chemicals, like carbon dioxide, too. But they don't just sit around. Gases are very energetic, and they bounce like crazy. The molecules bounce into each other without reacting, and they bounce against the walls of the balloon, which exerts pressure on the sides of the balloon. The air on the outside of the balloon also exerts pressure on the balloon, and we call that atmospheric pressure. We can measure atmospheric pressure using a barometer. This particular type is filled with mercury. Don't drink it or breathe it. It's pretty dangerous. So why use it? Mercury is the densest room temperature liquid, which makes it good for barometers. At the top is a vacuum, and the atmospheric pressure, all the atmosphere from Earth's crust to space, is pressing down on the liquid in the basin. When the atmospheric pressure rises, the mercury adjusts to the increasing pressure by moving up the tube. This creates equilibrium between the internal and external pressures. When the atmospheric pressure decreases, the mercury level drops to maintain equal pressure. This kind of barometer is read in millimeters of mercury because it measures the change in height of mercury inside the barometer. But this isn't the only measure of pressure. No, that would be easy. In addition to millimeters of mercury, there are pascals, which are usually measured in kilopascals and are the SI unit of pressure. There are atmospheres, or ATM, where 1 atmosphere is standard. And lastly, the torr, which is basically another name for millimeters of mercury, so go ahead and forget about it. You can convert between the different units. Standard pressure for SDP is 760 millimeters of mercury, 101.3 kilopascals, and 1 atmosphere. Just use a bit of dimensional analysis to move between units. If you had 825 millimeters of mercury and you needed to know how many kilopascals you had, you could use dimensional analysis to solve this. Start with what you're given and put kilopascals as your answer units. Knowing that there are 101.3 kilopascals when there are 760 millimeters of mercury, you can set up a conversion factor. And the answer is 110 kilopascals. So let's see how changing pressure affects the gases. You can change pressure by adding or removing moles of a gas, changing the volume, or changing the temperature. Particles are moving around, hitting surfaces, and creating pressure. When you add more moles of a gas, there are more particles hitting the surfaces, and therefore, the pressure will increase. In this container, the only thing that will change is the volume. When we cut the volume in half, from 1 liter to half a liter, the pressure will double. Temperature is actually a measure of the kinetic energy, or movement of the particles. When we add heat, we increase the kinetic energy, causing more collisions and raising the pressure. Now, speaking of temperature, Americans get a lot of crap from the rest of the world because we don't use Celsius, but it turns out Celsius isn't all that great either. Scientists prefer to use Kelvin. No, not Kelvin, Kelvin, because it goes to absolute zero, where the kinetic energy of atoms is zero. Well, theoretically, it's zero because the atoms will stop moving. But Kelvin is also better mathematically. If the temperature rises from 10 degrees to 20 degrees Celsius, it appears to have doubled. But if you convert those numbers to Kelvin by adding 273 to each one, you'll see that the numbers haven't doubled at all. Kelvin is accurate when it comes to proportions, so use Kelvin in your calculations. Now, to go from Kelvin to Celsius and Celsius to Kelvin, you just need to remember to subtract 273 to get Celsius and add 273 to get Kelvin. Now we're ready to learn some gas laws. Before we dive in, you need to know what the 4 variables of the gas laws are. We have pressure, temperature, volume, and moles. To see how one variable affects another, we have to hold the other 2 variables constant when we test them. First, we'll look at pressure and volume. We'll hold moles and temperature constant by using a sealed container and consistent temperature. And just like we saw earlier, when we decrease the volume, the pressure increases. This is an inverse relationship, which means the variables will be on the same side of the equation and the constant will be on the opposite side. Here's what that looks like. Pressure times volume equals a constant. Now, to see where Boyle's law is coming from, we need to look at the starting pressures and volumes and the finishing pressures and volumes. To tell the difference, we'll use a 1 for starting and 2 for finishing. Mathematically, we can use substitution to put these 2 equations together because they both equal the same value, K. And boom, that's Boyle's law. Let's try actually using it. A syringe is filled with air to 60 milliliters at 1 atmosphere. Then the syringe is sealed and compressed to 20 milliliters. What is the final pressure? We'll use Boyle's law, and we can rearrange the equation now or after plugging in the numbers. It doesn't matter, but for neatness, I'm going to rearrange it now. I need the final pressure, or P2, so I'm going to get that isolated by dividing both sides by V2. And then we just clean it up. Now we'll plug in the data, and you get 3 atmospheres. Do a concept check to see if it makes sense. Volume went down, pressure went up. That's inverse. Yep, seems reasonable. The next law looks at pressure and temperature, keeping moles and volume constant. It's sometimes called Gay-Lussac's law. Look, I don't speak French. I don't know how to say this dude's name. Sorry, dude. We know that when temperature increases, pressure also increases. This is a direct relationship, which means the variables will be on opposite sides of the equation. Pressure equals temperature times a constant. Now when we compare the before and after, we use substitution again to get Gay-Lussac's law, but it's a little easier to do the substitution if we get the K by itself first. Then we'll use substitution and boom, another law is born. Let's try a problem. A flask filled with carbon dioxide is heated from 10 degrees Celsius to 40 degrees Celsius. The starting pressure was 98 kilopascals. What's the final pressure? We're using Gay-Lussac's law and we need to find the final pressure, so let's rearrange the equation first. We'll just multiply both sides by T2 and clean it up. Now we'll just fill in the data and calculate. But be careful. Use Kelvin instead of Celsius and make sure the final temperature is on top and the initial is on the bottom. And then you get an answer of 108 kilopascals, or if you use sig figs, 110. Have you ever put a balloon in a freezer? Pull it out after a few hours and you'll find a shrunken balloon. As it warms up, it'll come back to full size. As temperature goes down, volume goes down. This is a direct relationship. This is essentially the same as Gay-Lussac's law, except we're using volume instead of pressure. So if you rearrange the equation and then use substitution, you get Charles's law, V1 over T1 equals V2 over T2. Let's try a problem. A balloon is filled with 1.5 liters of air at 20 degrees Celsius, then placed in a freezer until it reaches a temperature of 5 degrees Celsius. What's the final volume? Well, let's rearrange Charles's law to find V2 by getting rid of T2. We plug in our data, after we convert to Kelvin, of course, and you get 1.4 liters, which makes sense because volume and temperature are directly related. Now take a look at Boyle's law, Gay-Lussac's law, and Charles' law all together. We can combine these 3 laws together as long as we hold the number of moles constant. It's amazing and so, so beautiful. 5.36 liters of nitrogen gas are at negative 25 degrees Celsius and 733 millimeters mercury. What would be the volume at 128 degrees Celsius and 1.5 atmospheres? We're trying to find final volume, so let's rearrange this equation to get the V2 alone. We just have to multiply both sides by T2 over P2. And when we do that, we get this pretty equation. Now we can plug in the data, being sure to turn Celsius into Kelvin, have the same type of pressure units, and calculate. I chose to turn atmospheres into millimeters of mercury. The final volume, in this case, is 5.57 liters. Now, combined gas law is great, but what about moles? Hello. Before we add it, we need to figure out what its relationship is with other variables. Let's use volume to figure out the relationship. As you increase the number of atoms in a balloon by blowing air into the balloon, the volume increases. The pressure is the same because the balloon can expand, the temperature is the same, only moles and volume have changed, and they have a direct relationship. Now, because moles and volume are directly related, just like volume and temperature are directly related, we can put the number of moles, or N, next to temperature. But now we're holding nothing constant, so let's hold one entire side constant by setting it to the STP values and call it R. And we can get rid of the division by multiplying on both sides. And we don't need those subscripts anymore. And you get Pivnert, the ideal gas law. So much beauty in such a small equation. But let's talk about what R is exactly. R is calculated from P2V2 over T2 times N, and it's all set to standard temperature and pressure. So 101.3 kilopascals, 22.4, which we got from every mole of a gas at STP is 22.4 liters, 273 Kelvin, and that's just set to 1 mole. And what you get when you actually calculate those numbers is 8.31 kilopascal liters per Kelvin mole, which is really fun to say fast. Now, because there are different measures of pressure, that means there are also different values for R, depending on which unit of pressure you use. So if you use atmosphere, R is equal to 0.082 atmosphere liters per Kelvin mole, and if you use millimeters of mercury, then R is equal to 62.4 millimeters mercury liters per Kelvin mole. Again, say that one fast. Anyway, the point is, make sure that you check your R value that you're using for your problem so that it matches up with your pressure. Let's try a Pivnert problem. At what pressure would 0.15 moles of nitrogen gas at 23 degrees Celsius occupy 8.9 liters? Well, we're going to need to use Pivnert, but we're trying to find pressure, which means doing a little rearranging. You just have to divide both sides by V. Now we plug in the data, and I chose 8.31 kilopascal liters per Kelvin mole, but you could have chosen any of the other R values because it didn't specify what type of pressure unit was necessary for this problem. So I picked 8.31. Now you calculate it out, and you get 41.5 kilopascals, and that's it. Pivnert's actually one of the easier equations to use. I hope you enjoyed this episode of Teacher's Pet. Don't forget to like and subscribe.